our invited speaker today, and I've been practicing for this, but I'm sure I'm going to get it wrong. Kyunghyun Cho?
Yes.
Does
Yes.
Cho. Anyway, you all know him. So Kyunghyun Cho is an assistant professor at New York University, and also a research scientist at FAIR. I don't know how you can do both, but and you also said you've been trying to find the balance between life and work, and now I understand why it's hard for you, but it's impressive. So you probably all know Cho's work from various different fronts. So he's been involved in work, seminal work in machine translation and also image captioning. So some of the papers that we all cite on attention for machine translation using sequence models, attention for image captioning, and many other things that I won't even try and list. An impressive number of citations, but also number of papers, especially considering that you finished your PhD only 4 years ago. Is that right?
Yeah,
Yes.
4 years. Now slightly over, but
Slightly 4 years. Yes, I also didn't know, and I found out from your website that your PhD is from Aalto University in Finland, and also your master's. And after that, I worked with Yasho Benjo at Montreal University. And from 2 years ago, you joined New York City?
3 years.
3 years ago. Yes. So thank you for agreeing to give a talk. Looking forward to
Thank you.
hearing.
Thanks for the generous introduction. So, yeah, today I thought I was going to talk about two kind of very disjoint but related topics. And first one is on the how to do the parallel decoding instead of doing the usual way of doing the sequential decoding. And then the second one is going to be on the meta-learning for multilingual translation. And then coincidentally, I think the second one is related to one of the topics at the workshop at the moment, I think, low resource things, so because I'm going to talk about the extremely low resource case, but still low resource and then not the unsupervised one. But let's talk about the parallel decoding first. Oh, actually, so I thought it's always better to talk about something that has not been published or was rejected, right? So those are the interesting ideas. So the first one is one that was rejected from ICML, and then it is now under review in another conference that I guess I'm not supposed to reveal. So, well, it's already on archive. So, and then I think, it's going to get in this time finally. But let's talk about the parallel decoding. So, when we think about the neural sequence modeling, so it's very straightforward, supervised learning problem. We have some kind of arbitrary input X, and then the goal is to build a model that's going to map that arbitrary input X into a sequence output. And I'm going to call it Y, and then it can have variable, the length can vary from, let's say, very small to very long, and then it could be anything. But generally, we think of the natural language sentence, and then we think about the discrete tokens here. And what we want to do is in neural sequence modeling is to build a neural network, and then that neural net is going to estimate a distribution over all possible sequences given the input. So we try to get the log P of Y given X, and then essentially this is the one, let's say, equation that explains all the machine translation, speech recognition, like anything that you can think of, image captioning and so on. So one major difference, departure from the usual classification setting, is that there are complex, strong dependencies among the tokens in the output. So for instance, if let's take an example, if I say more than half of residents in Korea speak, and then I ask you, okay, which words should follow, then everyone will be able to tell me that is Korean out of, let's say, millions of the words that are possible. And somehow that's the only thing likely, and without even knowing any kind of context, because you already have captured that kind of strong dependency in the output. And then usually in order to capture those strong and complex dependencies, what we have been doing is to use the autoregressive sequence modeling. So we're going to rewrite the distribution over all possible sequences into a product of all the conditional distributions, or the probabilities, where each conditional is essentially to try to predict what's going to follow given all the previous tokens. So very straightforward, right? And then the nice thing is that it actually gives us a very nice way of sampling the sequence, computing the score for the sequence, and so on. Sampling would be, let's say we start from the beginning of the sentence symbol, and then we're going to sample the first word. And then given the first word, we sample the second word. And given the first two words, we're going to sample the third one. Given the first three words, we're going to sample the fourth one, and then all the way until the end of the sentence symbol is sampled. So this is great. And then, this approach has been extremely successful. All the, translation systems that are translation services that are being provided by, let's say, major tech companies as well as the translation service companies all use the exactly same paradigm. And then, they are in production. And then, some of you who use the Android phones, in fact, this model is being run on your phone whenever you use some kind of Google Translate related services. So that's pretty nice. Except that it's actually not that great because it's actually difficult to do the exact decoding. We don't really know how to find the translation that exactly maximizes the score that our neural net is going to compute. And then that's why we usually resort to some kind of approximate decoding algorithm. We usually do the greedy decoding or the beam search with the small beam width. But we don't really know how well those work, except for the fact that when we use it, it seems like it's doing pretty well. There are some there have been some recent papers showing that those approximate decoding algorithms are doing pretty well. I think that Jan, you wrote one paper recently, right? But even then, it's actually that exactly, we're not, let's say, we don't know quantitatively exactly, how far the gap, how large the gap is, and how to actually narrow the gap either. And then even if we use the approximate decoding algorithm, the decoding is inherently sequential. So we have to start from the left or right, so at one of the extremes, and then we need to decode one step at a time. So if you commit to something in the early stage, even if you do the beam search or so on, we cannot really redo the things that we have committed already. So then of course, all these problems are going to automatically go away if we try to impose some kind of conditional independence among the tokens in the output. So we're going to drop the dependency on all the previous tokens. Then suddenly all these the issues go away. And then how it's great. We can actually do the exact decoding because we're going to consider each token separately, and simultaneously, and then it's completely parallelizable because what we are going to do is starting from some arbitrary input, we're going to feed it through some kind of neural net, and then from there we're going to just generate the entire translation altogether. That's great, right? But then why aren't we doing this? Because that's too good to be true, that doesn't make any sense. The model will not be able to capture all those strong dependencies in the output tokens. So we need somehow a way to model these dependencies in the target side. And then one way that people have been doing with all those probabilistic graphical model is to introduce the latent variables, right? So we're going to introduce some hidden variables, Z, and then those hidden variables are going to capture all the dependencies in the output. And then now if we can train this model, then we may be able to find some nice, let's say, intermediate point between the completely conditionally independent model and the autoregressive model. But unfortunate thing is that this is also not that easy, right? So the sampling procedure is really easy because we're going to start from some arbitrary input X. We're going to compute the posterior distribution over the latent variable Z, and then we sample the entire sequence from this. So that's good, except that in order to train this model, we need to be able to marginalize out the latent variable Z. And then that's almost always intractable, and then there's no, let's say, generic algorithm that allows us to train this model in any kind of tractable time, unless we put some kind of interpretations on these latent variables, and then based on the interpretation that we impose, we can actually come up with some nice approximate inference or the learning algorithms. And then recently, so earlier this year at iClear, the Jiatao Gu and his colleagues, when Jiatao was at the Salesforce research, showed that we can actually train this kind of model by imposing the latent variables to capture the number of repetitions each of the source token will, how many times each of the source token is going to be repeated in the translation. So that's like the fertility from the IBM model. I don't know which one was it. I don't even remember. There are too many, model 1 to 5, right? But so then the idea was that, okay, we start from the source sentence. Let's say we had 2 tokens, and we are going to have the two Latent variables as well. So each one of them corresponding to the corresponding source token. And then this Latent variable is going to correspond to how many times the corresponding source token needs to be repeated in the translation. So let's say the first one had to be repeated once, and then the second one had to be repeated 3 times. Then we're going to initialize the decoder with the 1 copy of the first source token and the 3 copies of the second source token. And then given now all these, we train a model to generate the target translation simultaneously in parallel. So without modeling any kind of, let's say, dependencies directly, we're going to assume that this is enough to capture all those dependencies in the output. It sounded kind of too good to be true when I was reading the abstract of this paper. It turned out that it actually works pretty well. So what they did was to use the external alignment model. So they used the fast align to find the extra supervision signal for all these Latent variables. So this part, the part where you compute the Latent variable configuration given the source sentence, was done by the extra supervision using the fast align on the, let's say, parallel corpus. And then once that is trained, they trained only this part initially to do the translation. And then once everything was done, what they did was to fine-tune everything with the reinforcement learning algorithm, policy gradient algorithm called reinforce back then. I still cannot believe that it actually worked. And then I couldn't believe it back then either. When I was reading the paper, I was like, oh, no, it doesn't make any sense. Of course, there are a lot of, let's say, small details that had to be followed exactly in order to make this model work. But until I read the experiment, it was actually difficult to believe that this one was going to do anything. It turned out that it actually does work pretty reasonably. So in the very small corpus of the IWSLT 16 English to German translation task, when they trained this model and then did some kind of, let's say, very expensive, let's say, Monte Carlo sampling and then rescoring with the autoregressive model, they were able to get to the score, get to the blue score that is actually within, let's say, 2 blue score or the 1.5 blue score from the state-of-the-art autoregressive model. With the, let's say, I don't know, latency that was, let's say, less than half of the autoregressive model. And then that was actually really the first convincing results that I've seen with the non-autoregressive machine translation system back then. Now, but if you read the paper, and then I highly recommend you to read the paper, because then you see that, okay, how much effort goes into, like the building of this neural net, because there are so many different loss functions that need to be combined, so many different, let's say, ways of initializing the, like the initial state of the decoder and so on and so on. It's actually a very involved one. And then my PhD students and I started to think that because we were working on the non-autoregressive model without any success by then, but whenever you have that kind of convincing result published somewhere, then you kind of renew your interest and the excitement and then trying to work on it. And then we decided to, okay, so we're going to follow the same type of the Latent variable model instead of the autoregressive model, but let's try it from scratch. Let's try to start from scratch, and then let's see, if you can come up with a kind of, let's say, different principle that's going to allow us to train this kind of model better or more easily. So we started by, okay, imposing some of our own interpretation of what the Latent variable should be. And then the first thing that we decided that, okay, so these Latent variables or the Latent sequence is going to be the translation. That was the first thing that we thought. Okay, so what we're going to do is, why not? So our Latent variable, Latent sequence is going to be exactly in the same space as the actual target sequence. So that's the first thing we imposed. And then we decided to assume that, okay, there are multiple layers of Latent sequences. So now, and in that case, what happens is that now these Latent sequences are in the same space as the translation itself. And then we have the multiple layers. And from here, if we decided to simply share all these conditional distributions across multiple layers, it somehow looked very much like trying to refine translation little by little over time. And then we're going to use a single neural net for modeling all these distributions. And then once we do that, the interesting thing is that the number of the layers of the Latent sequences can vary as well. And then that can vary with respect to the input. So, based on the input, if the input is simple enough, we're going to just run this, let's say, inference procedure only a few times. If the input is complex, we're going to run the inference procedure several times. So what is our nice generative story is that it is an iterative refinement. So first, we're going to refine it over and over until we see that the translation is now reasonable. So we start from some arbitrary input. We're going to feed it into some kind of neural net that's going to get me my initial translation. And then this initial translation is going to be going to the next stage, but it's the same neural net that takes as the input the previous translation and the input, and then it's going to try to refine it. So get us the better one. And then we can apply the same neural net over and over, and then we can ensure that the translation gets better and better. Now, how do we ensure that? That's actually the big question, right? So it turned out that there are two ways to train this model, or two strategies that we can use. And then we had to use both of them. And then the first one is just usual end-to-end training. It's a neural net, right? Deep neural net. What do we want? We just feed it through, do the feed forward, and then do the back probe, and then update the parameters, and then that's what we usually do. So the end-to-end training is possible in this case. It's just that there are, let's say, output at every layer. So we want to ensure that every layer is going to output something reasonable. So what we do is, after the first, let's say, refinement, we try to ensure that the output is going to be close to ground truth, and the second refinement, and then for every layers of every stages of the refinement, we're going to put the loss function there. And then without doing this at every layer, we cannot really guarantee that it's going to try to get a good translation every time, right? So who knows? It might decide to use those intermediate translation not as a translation, but as some kind of arbitrary storage, and then we don't want that to happen. And then the second strategy is viewing it as a denoising autoencoder. So some of the surprising results that we know already from the 2011, 12, and 13 is that the training denoising autoencoder in fact allows us to capture the gradient field or the score function of the underlying distribution. So if you train a denoising autoencoder on this kind of data set where the data points were completely concentrated on this spiral, if you train a denoising autoencoder, then that autoencoder learns this kind of gradient field that brings us toward the manifold on which data were concentrated. And then once we train this kind of denoising autoencoder, as long as we start from somewhere reasonable, we can apply this autoencoder over and over to get to the point where the underlying distribution has had a high probability. And then we can apply this idea exactly, like as it is, but make it conditional. So what we're going to do is, we're going to start from the ground truth translation. We're going to corrupt it using some kind of corruption function. So the corruption function, we can manually design it, or even you can even learn this corruption function. We just use a very standard denoising, let's say, corruption function for the denoising sentence autoencoder. And then this corrupted version is going to go into this neural net that does the refinement together with the input, and then this neural net is trained to denoise the output target. And then we can train it as a single layer, or we can put this into a part of this end-to-end training as well. And then what we found to be really useful was to mix these two objective functions. So one is the end-to-end objective function, the other is the denoising autoencoder objective function, as stochastically over the, let's say, multiple iterations of the refinement. So we're going to run the refinement for, let's say, L steps during the training time for each of the examples. And then for at each layer, we're going to toss the coin with which is going to land head with the probability alpha L. And then if it lands head, then we're going to use the end-to-end training criterion for that layer. If not, we're going to use the denoising autoencoder criterion. So why did we do that instead of just doing both? It was just the first thing that came to our mind, and then that's how we implemented it. It worked pretty well, so we stuck to it, but I'm pretty sure you can do a lot of different things. And then now the interesting thing is that in this case, there's absolutely no the extra thing that you need to do. All you need to do is you really just write down this criterion and then just train the model as usual. And then it's going to actually, you will see that the loss function goes down and the blue score goes up. So one thing that we forgot to put in the paper, but I'll just tell you now, is that in this case, the interesting thing is that the loss function on the validation set, in fact, immediately starts creeping up from the very early stage of the training. But if you look at the blue score of the resulting translation on the validation set, blue score also continues to go up. So in other words, I'm not entirely sure whether this loss is the issue or this loss is the issue or the entire thing is the issue, but there is some issue with this objective function that kind of doesn't tell us how well it's doing in terms of generalization, and then we have to use some kind of proxy measure. But it turned out that all we needed to do was just check the blue score, so that was fine for translation. But that's kind of one caveat, that I have absolutely no idea why that happens, and then I have absolutely no idea on how I can explain it. But that would be the one thing that kind of, let's say, it would be nice to be investigated in the future. So we did some experiments. So on the machine translation, we tried on the low resource machine translation. So translation between English and Romanian. So it's a pretty small data set. And then we trained the transformer, the state-of-the-art autoregressive model, and then, it gets a decent blue score, but it's pretty slow, especially on GPU. It can only decode about 43 tokens a second. That's on the source side. And then we trained our model, which is going to do the iterative refinement. And then the nice thing is that once we train this model, we can actually change the number of iterations, like however we want, right? So if we train our model, and then if we just let it do the one step of refinement, then we see that, okay, blue score is pretty horrible. The translation is kind of the same, impossible to understand, but we can do the we can translate almost 700 tokens a second on just a very usual GPU, even without any kind of optimization. But as we let the model refine further and further, we do see that the translation quality goes up and up and up, but at the expense of the decoding efficiency. And then we can actually come up with a very simple adaptive rule that is, if the model does a refinement and then the translation stays as it is, we're going to simply stop, right? So we just check the convergence, and then we can actually get the best of the both worlds by, retaining over 100 tokens a second decoding efficiency while getting the translation quality that is about 90% of the autoregressive model's quality. And then we decided, okay, so let's try to increase the scale. So we tried it on the English and between the English and German. And then what we see is that, unfortunately, as the size of the data set grows, this model actually doesn't do as well. So we could only get up to the 80% of the translation quality of the autoregressive model, the state-of-the-art baseline. Although, we were able to achieve the 2x decoding speed up on GPU. So it seems like there is a lot to be done in this direction. And then now the question is, okay, does it actually improve the translation quality every time you let the model refine further? And then it turned out that that's actually the case. So this is the number of the refinement step in log base 10. So it's actually a lot of steps. And then this is the blue score, and then this is on the German to English and English German. And then you should only look at the solid curve, because this dashed curve is even more approximate version of training. And then if you look at the solid curve, really after training, so it was trained with about 4 iteration steps only. But what you see is that we can actually run all the way to 100 refinement steps, and then we do see that although there is a diminishing return, but there is a return as we let the model refine further and further. And that's quite interesting observation. So what does it actually do? Let's look at some of the examples. So this is a source sentence in German, and then this is a reference. I was told by some German native speakers that this is not really the greatest translation you can make, but that is the example from WMT, the use test. So I'll just stick to that. And it's not like I speak any of these languages well enough. So this is the first rough translation that our model makes. And then if you focus on this underlying parts, this underlying parts just doesn't make any sense initially, right? But then we're going to let it refine further and further. So after 4 steps or 4 iterations of refinement, we do see that it is starting to make a bit more sense than the initial translation. If you let it refine even further, let's say after 8 iterations of refinement, we do see that now it actually does, produces a reasonable translation. And then the similar example can be found really easily. These are not even cherry picked. We just randomly selected it, looked at all those refinements, and then we saw that it always learns how to little by little change. So add few words or remove some words, sometimes reorder some words, in order to make things into a more syntactically and semantically correct translation. And we thought, okay, so this is good, but as in the introduction, I also worked on the caption, so we decided to try it on the image caption generation as well. So unlike the earlier work by the Salesforce team, like this model does not require any kind of external tool, so we can actually train this model on any kind of arbitrary input. So we decided to try the image caption generation. It's a very, very horrible task. I don't think anybody should work on the image caption generation really ever. too many follow-up papers. Unfortunately, we were actually doing it for fun initially, but it turned out that is a big thing. So if you train this model, and then if you look at the blue score, which is a horrible metric for the caption, like the assessment, because like the image has a 2D grammar, and then like the text has 1D grammar. So unless you have, I don't know, like exponentially many, let's say in terms of the dimensions, the references, it doesn't make any sense to actually use blue, I think. But anyway, so you get about 25 blue score. And then if we train our model, we can get up to, let's say, 85% of caption quality in terms of blue, with up to, let's say, 5x decoding speed up. So that was nice. And then let's see how it actually does it. So this is the input image where there is a tennis, two people are playing tennis in a tennis court. The initial caption is pretty raw. It has all the necessary stuff, but it just doesn't sound right. A woman standing on playing tennis on a tennis racket. But if you look at how this caption is refined each time, you see that notice that playing probably is not necessary here. It's going to replace the playing with a and then on is not necessary, so let's remove the on. And then it moves its focus into the, let's say, tennis racket, and then it says that, so I already said tennis course, so like why say tennis again, right? And then eventually it gets a pretty decent caption, and then we see this kind of behavior almost always. So this is another example where there is a bus parked in a parking lot, and then the initial version, it doesn't really make much sense. But as it refines the caption, it gets better and better, and it sometimes gets even some of the semantics that was missing from the initial translation, because we let our model look at the source every time together. So the black was not there, but now it shows up from the second iteration, and eventually it does get a pretty decent caption. So that was my part one. I probably need to speed up a bit. But the conclusion of the part one is that we can really use these kind of Latin variables to capture output dependencies, and then like often we can do it much more efficiently, not necessarily effectively. And then somehow different interpretations lead to a different learning and inference algorithm. So the earlier one by the Jiatao Gu, they interpreted the Latin variables with the idea of the fertility, and then they ended up with a learning algorithm that requires the auxiliary supervision, and then decoding algorithm that is based on the noisy parallel decoding. And then our work, by imposing that the Latin sequences are in the same space as the actual translation, we came up with the the iterative refinement, and then that led to the conditional denoising. That was a learning algorithm for us. And then simultaneously, there was another paper from the Google Brain team, Google Brain, or I don't know, Google AI, I don't know, one of them, right? And then what they did was that, Latin sequence is going to be a compressed form of the original sentence, as in, so they constrained the length or the number of tokens in the Latin sequence, and then they built in the hidden autoregressive inference there. So they're going to do the autoregressive inference on a much shorter sequence, and then from there, they're going to generate the translation directly. So the generation quality seems to closely, if I'm being optimistic, track the autoregressive model's quality, but probably not. And then especially the generation is significantly faster on GPU. So there is some potential for using this kind of model for the specialized hardware, unlike which can do a lot of, let's say, parallel processing. So some of the future directions I believe include can we mix non-autoregressive and the autoregressive paradigms? Because clearly this non-autoregressive model is not working as well as autoregressive model. But does that mean that do we have to abandon it? Probably we can find some kind of, let's say, mix, or the the intermediate let's say point between autoregressive and the fully non-autoregressive model. And then what I think is that this kind of non-autoregressive model might be actually much more suitable for the document level generation. So what we're going to do is we use this kind of non-autoregressive model to generate the seed or the sequence of seeds for the sentences, and then for each of the sentence, we're going to use the autoregressive model inside to generate a fluent sentence. If you think about it, the issue with the non-autoregressive model is that the sentences that it generates are not fluent, because it cannot really get the order correctly because the, like all those strong dependencies are really difficult to capture. But the autoregressive models can do it really well. So we let the sentence order to be decided by the non-autoregressive model because the sentence orders are much more, let's say, relaxed than the word orders. Because if you make a mistake in the word ordering, it doesn't make any sense. But if you make a mistake in the sentence ordering in a gigantic document, it's often okay. So it seems like there are many exciting future directions, but we'll see how it goes. I have been known to be wrong as well a lot of times. But so this was the part one. Now I'm going to move on to the meta learning and multitask learning. Do you have any questions here? Yes. Yes.
I have a question about the end-to-end training.
Okay.
So the latent variables are discrete, right? What's the trick to make it do end-to-end training? Is that the lower bound thing you're talking about?
Yes. So yeah, exactly. So in this case, if you do the backpropagation, you get stuck here at some point, right? Because this is a discrete, let's say, sampling procedure. So we tried actually two things. One is to get a very loose lower bound by just doing the argmax and then not backprop through it. So that's going to give us the extremely loose lower bound. And then that is the one where the training works, except that it actually starts to fail eventually as we do the more and more refinement. So at the end of the day, what we did was to stochastically estimate this thing using just like the sampling with the many samples. And then in that case, it was fine to just put the loss here and then not backprop through the sampling procedure. But I think we can actually probably do much better with the like the more tighter lower bound with the lower variance than the sampling. I think we should be able to do that, but I just haven't figured it out. Yes?
Have you looked at the attention weights after all the refinements? Because it seems in your image captioning that the attention looks better, right? It stopped doing some repetitions and so on.
Right. So no, we haven't really looked at it. So we use the transformer inside, and then like the transformer,
okay.
The visualization of the attention is always very, very confusing. So
sure.
yeah, we could have used the LSTM based one and then see how it goes, but we haven't had time to do that.
Okay.
Yes.
Is this a way of learning how to do beam search with a neural network?
Yeah, I guess so. So I mean, like, that's actually a really interesting point. In a sense, so I forgot to put the figure every time. In a sense, like the number of steps changes according to the complexity of sentence or the first sentence, and then it tends to like the number of iterations like increases as the, let's say for instance, length of the sentence increases roughly logarithmically. It's not like linear, so it's more beneficial. But then it's slightly different from beam search in the sense that we can really look at the entire sequence and then make a decision. So it's somewhere in between. But that's actually a super interesting point. So the answer is that I don't really have an answer. Yes. Yes, I got it.
Yeah, in order, the non-autoregressive translation is basically a sequence classification. So you need to estimate the length of the sequence somehow. So my question is, how do you do that, and how do you do that, especially in case of the images?
Yes. So it turned out predicting the target length given any arbitrary input is relatively straightforward. So we just have another model that looks at that actually shares this neural net representation that just predicts the target length. And then we do it in a classification way. So we have the bin of, let's say, I don't know, like 100-way softmax classifier that's going to predict the length. And then we do get, let's say, bimodal distributions often, but there's always a dominant thing. And then that actually does correspond to the true length very, very closely, even for images. I know, it's kind of crazy, right? Yeah, I still do not believe that, yeah. But it does work pretty decently. But when we use the ground truth or the reference length during the inference time, then it does get better. Little. Okay.
So you have done this with transformers, have you done this with this?
So we haven't. So we should. So the reason why we use the transformer exclusively is because so the Jatavu and others, the Salesforce research paper was using transformers, so we wanted to ensure that almost everything is like on the same kind of setting. That's why we use the transformer. And then also there is the advantage of, so if you use the LSTM, there is a sequential processing, and then that was the one of the things that we wanted to eliminate. So using transformer made sense. We initially started with the convolution, but I think the convolution should work as well.
But do you think LSTM would still make sense?
Yeah, I think so. It is probably going to work much better than this. It's going to be a bit slower. So the one issue is that getting the order is really difficult for this kind of feed-forward architecture like the transformer. But the LSTM or any kind of recurrent neural net can learn to count, so that can be very, very beneficial in deciding, like which word to put in which location. So I think using LSTM is going to be better, but it's going to be slower. So it's largely about a trade-off. Yes.
Do you always put the correct numbers in training of words in there, or do you also noise that?
So during training, we always put the correct number of the tokens in the target site. We tried actually adding a bit of, let's say, like a bit of the, let's say, few more words at the end, because like we thought that might be useful in the inference time when the length prediction is not perfect. It turned out that that doesn't really make much of a difference. Actually, no difference research. So yes. So this was, like how to generate something from the model, and then you probably have noticed that it was very generic in a sense that I didn't even show any kind of neural net architecture there, right? So there was really like the gray box, and then you can plug in whatever. And then now let's talk about how to train that thing in a slightly more exotic way. So we're going to focus more on the training of these neural machine translation systems. So this one is currently under review. And then this one, I don't think we even posted on archive yet, but if you want to look at the manuscript, just email me, I'll send you one. So it's about the low resource machine translation. So if you think about the multilingual translation, traditionally there wasn't really an option before the neural machine translation arrived here. So if you had a parallel corpus, then you are going to build a system for the very specific language pair in a specific direction. If there's no parallel corpus, then you're going to do some kind of pivot-based translation, going through another language for which you have resources. And then, like often in this case, there's almost no knowledge transfer across different language pairs or the different languages. But with the use of the neural net for machine translation, we started to see from the 2016 many papers on building a multilingual translation system that's going to share the representation space. And then, sometimes, like people, including myself, claiming that like this has to be beneficial because we use the same kind of space, and then this neural net is going to find the shared structure underlying all these languages, and then, like they have the positive language transfer and anything, but nothing was really, let's say, convincingly presented. Although there were some advantage of having a much smaller model for the same number of language pairs. So largely what we have been doing is doing multitask learning for the multilingual translation. So one direction has been to build a separate encoders for all the source languages and then separate decoders for all the target languages. And then what we're going to do is, given a pair of examples, okay, regardless of which source and which target language it is, all you need to do is just pick the corresponding encoder, pick the corresponding decoder, you're going to plug them in, train it together, and then you can actually train this kind of model for any number of languages with all the resources you have. And then eventually what you can have is that one of the encoders can be a convolutional neural net that's going to take as the input an image. One of the decoder could very well be the wavenet that's going to just generate a speech. That one, nobody has done it yet. But the image, the multimodal machine translation, has become a thing starting from 2016 by the people actually who are sitting in this room. And then another direction, which is much more on the language side, is to use a single encoder for sentences written in any of the source languages, and a single decoder for any of the target languages. So, it's called universal encoder decoder. I don't know. I'm not the big fan of the universal there, but someone in this room actually decided to call it universal. So okay, we'll just stick to that name. And then. So all we need to do is ensure that the vocabularies single vocabulary is shared across all the source languages and then all the target languages. So we need some kind of, let's say, a function that's going to map the sentence or the tokens into the shared tokens across all the languages. And then once that's done, all we need is just a single network that you just train. And then you need to just inverse the process of the, let's say, vocabulary matching at the end. And then the nice thing is that we can use all available language pairs without having to worry about if I have the multi-way translation or the bi-way translation, tri-way translation, who cares? We're going to use everything. And then does it work? It actually kind of does work. So this is the one example from the paper last year done by Jason Lee. And then, like there, what we did was we built a neural translation system that is fully on the character level. And then we trained four systems first, going from German to English, Czech to English, Finnish to English, Russian to English. And then we trained the multilingual system. This is just one network. Just what we did was to aggregate all the data and then feed the data to train the single model. And then now this system can translate from any one of these four languages to English. So this system has, let's say, a quarter of the parameters only. And then when we look at the blue score, the automated translation quality metric, it was pretty reasonably better than the single system models. And then when we looked at the human evaluation, both fluency and adequacy, I didn't put the adequacy here, but because it actually had essentially the same kind of trend, the multilingual system was much more preferred by the human evaluators. So this was good. Well, it's not perfect, so it often fails to translate between a pair of languages that were not seen during training, but for those, let's say, observed pairs, it worked pretty well. And then, because we use a shared vocabulary, and then we do not give the indication of which language the source sentence was written in, we can actually make up all those, let's say, code switching, let's say, sentences, and then give it to the model, and then hope that this model is going to do some decent translation, and then it actually does it. So it's a German, Czech, German, Russian, German, and then we just feed it in, there was no such sentence, and then the system can actually do the translation quite reasonably. Actually, it's doing it perfectly. I think this translation is better than this English reference, but it does really work pretty well. But then, there are limitations of multitask learning that people really don't talk about that much. And then, the multitask learning is a very fascinating topic. When the Rich Caruana wrote the multitask learning as his dissertation in 1998, I heard that everyone thought that the multitask learning is going to be the one that everyone works on, except that nobody did for the, let's say, first 15 years or 10 years, until Ronan Colbert and Jason Weston wrote a paper and then published at ICMO, which just got the Tesla Time Award last week, showing that multitask learning may be beneficial. But then if you read that paper carefully, it actually says that actually multitask learning doesn't really help. It actually has that sentence, almost it's a slight paraphrase, but it almost says exactly that thing. And then recently there have been multiple papers showing that the multitask learning is useful for a certain configuration with a certain combination of the task. But I highly doubt, because I also have written the multitask learning paper, and then I cannot really recommend it to anybody at the moment because it's so difficult. So why is it difficult? First of all, it is especially difficult when the availability of the data drastically differs across languages. So one of the promises of the multitask learning was that by doing so, we are going to improve on the low resource problems. But the thing is, let's say if I have a very low resource problem and a very high resource problem, what's going to happen is that as we train this model, it's going to rapidly overfit on the low resource problem, while it hasn't learned anything on the high resource problem. So then we have to come up with so then we have to probably come up with some nice scheduling of the problems when we train. But how do we schedule it? So maybe, not scheduling, but maybe we need to do some kind of different weighting or something. Maybe not. Maybe we need to oversample the low resource case. I don't know. It's really difficult. It's extremely horrible to figure out those, this correct scheduling and the correct weighting. And then it gets worse and worse as the number of tasks increases. So when we worked on the multitask learning for the multilingual translation on both cases, it wasn't easy to actually make them work because the sizes of the data set kind of differ significantly across the tasks. And then there are so many possible ways to do it. It was very much of the art than science, or actually magic than science. It's not even art, it's very horrible, right? And then the second issue is that it actually does assume the availability of all the language pairs or all the tasks in advance. it actually, multitask learning does say that, okay, we have the multiple tasks, we're going to build a model that's going to solve all the tasks. And then if there is a new task or the new language pair introduced, then in fact, the most principled way is to retrain the entire model from scratch using the all the data sets that are available. So obviously, like this is not that great. So people have worked on using the transfer learning, especially in the domain of the machine translation recently. And then what they do is that, okay, train a model on the many tasks, and then they're going to freeze certain part of the parameters and then just fine tune it on the new task with a small amount of data. It sounds reasonable, and then that has been largely a successful strategy for many of the transfer learning and computer vision and so on, except that it's also not that trivial. So this is a table I took from the Zofel 2016. So they were doing the transfer. So this is a transfer setting. So they pre-trained the model on, let's say, a large resource. They're going to do the transfer, fine-tune it on the new task. If they don't do the retraining, it doesn't work. And then they decided that, okay, so they're going to retrain only the source embedding. So they changed the source language only. And then, it does something, 7.7. And then they decided, oh, maybe that's not enough. Okay, let's try to fine-tune the recurrent neural net on the source side as well. Okay, it got better. Target side as well. Maybe attention. Maybe we should also fine-tune the target side input embedding. Maybe output embedding. Wait, hold on. But there is a best point somewhere in the middle. And I'm pretty sure where the best point is going to change for every single transfer task that we're going to try, and also based on the network architecture that you have or the source problems that you have. So it's a very manual kind of thing that has no guarantee of like how it's going to work out. So some of the inconvenient truths, so to summarize them, especially for the multitask learning and transfer learning and the natural language processing or the machine translation, is that, okay, first, we rely on our intuition that all languages tasks share common underlying structures. Maybe, okay, maybe. And it also assumes that, like the multitask learning can capture those underlying structures if there are, and then share across multiple languages and tasks. Maybe. We hope that that's going to happen. We assume that, okay, multitask learned parameters are good starting point to fine tune for the new task. Maybe, probably, yeah, I guess. So the question is, okay, can we do it slightly better, slightly more explicitly by incorporating the fact that, okay, this model is going to be used in the future, in the test time, on a new problem. So we decided to look at the meta-learning approach, and then one of them is the so-called MAML, the model agnostic meta-learning, proposed last year by the Chelsea Finn and others from Berkeley. And then, like in this case, what we do is we're going to do the usual stochastic gradient, let's say, based learning, except that we're going to consider the fact that the found parameters are going to be fine-tuned on a new problem with a small amount of data in the test time. And then what that leads to is a just usual stochastic gradient, but at each update, we need to do two stages. First stage, we simulate how the learning would be in the future. And then we do the meta learning where we are going to actually backprop through that learning, potential simulated learning procedure, so that our parameters are going to be better at being fine-tuned in the test time. So that's simulated learning. So what we're going to do is we are going to assume that we have a lot of, let's say, different tasks, and then we're going to sample one of the source tasks, and then within that we're going to sample a mini batch. And then we use that mini batch to update the current parameters. So we have the objective function, we have the mini batch, we can compute the objective function, we can compute the gradient of the objective function with respect to the parameters, and then we can update the parameters, but we're not actually going to update it. So we're going to just simulate updating these parameters. So, and then let's say we can take any kind of n number of steps, but it turned out that just doing n1 is fine. And then we ensure that, okay, this is not going to deviate too far from the original parameter theta 0, but it turned out that that's actually not that difficult. All we do is we do the early stopping based on that. So this is our simulated learning stage. In the second stage, what we do is that we have simulated it. So, okay, we're going to take another mini batch from the same source task that we selected earlier. So this one. Then we're going to evaluate how the objective function of the simulated model on this new validation mini batch. and then see what the performance is going to be. So that's going to be this one. And then now with this one, we can now compute the gradient of the objective function on a simulated validation set with respect to the original parameter before the simulated learning. Then what it means is that if we want to find the parameter that's going to maximize the objective function on the validation set if we had taken the one step of SGD using a training set. So it's like, okay, let's try to do the learning and then see how well I'm going to do, and then try to ensure that my initial parameter is going to be as good as possible. So the most appropriate for SGD on those small amount of data. And then we update the meta parameter only. And then, like there is one big issue because we have to compute the Hessian, actually the gradient Hessian product. You can either compute it using the LOP or the ROP by the permuter, or you can just use a finite difference approximation there. And then we use the finite difference approximation, which worked really fine. Or it turned out that we could even ignore some part of that as well. So the nice thing is that at the end of the training, what we do is that we end up with this, like a nice meta parameter that should be better for the adaptation in the test. And then what we do is we're going to get a new small training set for the new target task, and then we just do the SGD, but we ensure that the new parameters are not going to be too far away from the meta parameters. So you can think of it as kind of putting the very strong prior on the parameters, such that the parameters are going to stay near the center. So the theta 0, the meta parameter is going to be the mean of the prior distribution. So why is it better? Why is it better than doing the multitask learning? So conceptually, you can view it in this way. So let's look at the panel B and C. So this is what we usually do with the multitask learning. So we have the, let's say, 3 source tests. We're going to find the parameter set that's going to solve these 3 tasks as well as possible. And then hope that starting from here, if we fine-tune the model for the new test, it's going to do better. So that's what we hope, right? So, and then, like, is that true? Maybe, maybe not. It depends. But on the other hand, with the meta learning, what we do is that we're trying to find the parameter set that's going to be easily adaptable for all the source tasks. And then, this point doesn't really solve any of these problems, but this point has a much better chance to solve the problem if it had been, if it's updated using the data set from those tasks. And then if all those problems are nearby in the points, that's the point where you want to find, not the point that is really close to a small subset of the problems. And obviously, it doesn't really work well with language-related problems, because it kind of assumes that the input and output are exactly the same across all the problems. But in the natural language-related problems, often we use a different vocabulary for the different languages, and then like a different target for the different problems. So what we did was to use one of those, let's say, multilingual or the cross-lingual embeddings. We used the one from the Jiatao, who worked on this one as well, called universal lexical representation, that is using the multilingual word embedding that is extracted in an unsupervised way. So we use all those Wikipedia texts for all those languages, and then we extract the multilingual word embedding, and then we use that as a part of the model. And then now you end up with a kind of meta neural machine translation system. So we did some I think, kind of extensive experiments. So we decided to use all the languages from the Euro part plus Russian. So we're going to translate always into English, but we're going to vary the source languages. So we go from like Bulgarian to English, Czech to English, Danish to English, like German to English, Greek to English, Spanish to English, Estonian, French, Hungarian, Italian, Latvian, something, so many of them, right? And then we kind of take them as reasonably high resource languages. So we're going to use the Europol, and then the Russian, another pair of corpus. And then as a target task, we're going to simulate some low resource language pairs. So we are going to use a Romanian to English, Latvian to English. So this is Latvian, so this is Lithuanian, I guess. Finnish to English, Turkish to English, and Korean to English. So we kind of, let's say, chose these to ensure that we have the diverse set of the target tasks, while the source tasks are kind of, let's say, all similar to each other. And then we're going to assume that we only have roughly about 16,000 target tokens, English side, and then that corresponds to roughly about 800 sentence pairs. So we want to be able to build a translation system that is going to be trained using only the 800 training examples. And then we use the, as I said, universal lexical representation obtained from Wikipedia. And then in this case, because we do SGD on this meta learning as well, so we need to now have a validation task. So we usually have the validation set to do the always stopping, but now we need a validation task to do the always stopping of the meta learning. And then we're going to use either Romanian or Latvian to see, like if the validation task has any kind of effect on, like the performance. So this is the general, let's say, overall, let's say, results. The first two bars, yellow and the red ones, correspond to the multitask learning. So we're going to do the multitask learning on all those language pairs and then do the fine tuning. And then the third and fourth bars, like the violet and the blue bars, they correspond to the meta learning. So we're going to do the meta learning and then fine tune. And then across board, we do see that the multitask, the meta learning is, like almost always beneficial. And then the difference is larger for some languages. For some languages, differences are kind of small. So for instance, in the case of Turkish to English, the differences are not that large. We didn't put Korean to English there because it really just doesn't work at all. Yes.
Are the differences for how much data is available in that language, or with how different that language is from the other?
Oh yeah, I'll get to this. So just one thing is that we always use the same number of examples across all these language pairs on the target side. So we're going to simulate the kind of scenario by sampling actually multiple times. So for each of the bar here, we actually run five runs of the experiments, and then this is actually the error bar. So it's pretty small error bar we see there. Yeah. So like what we see is that like it's really nice, and then with the meta learning on some of the data language pairs, we can actually get up to 65% of the fully supervised model, which were trained with the tens of thousands of orders of magnitude more examples than the 800 examples. So that was pretty nice. But interesting thing is that the effect of meta learning actually differs across different target tasks. So in our problem, okay, so one good thing is that as you have more and more source tests, it does better. But how well the target task does actually differs quite significantly. Romanian to English, it works really amazingly well. But if you look at the Korean to English, it really doesn't do anything. If the blue score is lower than 5, like it's essentially not doing anything. And then like we see that Finnish is doing okay, and then there's Latvian, and then there's Turkish, and then there's Korean. And then we didn't put it here, but it's in the paper, which is not available yet, but still, you can email me. Is that there is a dependency of the target task quality on the choice of the source test. So if we only chose, let's say, German and Russian as the source test, then the Latvian actually does better than Finnish. But if you use somehow the Spanish, French, Italian, and Portuguese, then the Finnish does better than Latvian. I don't know, maybe there is some kind of, let's say, language similarities among those that I don't understand. Yes?
I'm not sure, but this kind of relation with the type of language, for example, in this case you are saying that Spanish, French, Italian, and Portuguese improve the Romanian one. And this, of these 4-5 languages belongs to the Latin language. So I'm wondering if you, for example, mix Chinese, Korean, Japanese, probably the Korean is going to be better.
Maybe, yeah. So that's why actually we added the Turkish and Korean here, because they, especially the Korean, is very, very different from all these European languages, and the Korean is supposed to be language isolated as well. So we thought, okay, so would this kind of language that is very different from all the other languages also benefit from this kind of meta learning when the source languages are from all the European languages? And then, as we can see, no, right? The answer is actually no. So there is definitely those, let's say, language dependencies, but it's difficult to tell, like which ones should be used. And then, like in some sense, it also kind of betrays our linguistic intuition as well. Why would Finnish closer to these, like the Spanish, French, Italian, Portuguese than the Latvian is? I don't think there is any similarity actually between Finnish and these languages, except that they share the alphabets and some of the loan numbers. But somehow that helps. But they don't really help Latvian. Difficult to tell. But I think this might be an interesting way to actually study how the different languages are similar in terms of learning these systems. And then so this is the most important figure, I believe, is that, okay, let's just focus on the, we can focus on everything. So, okay, so the purple ones correspond to doing the multitask learning and then doing the fine tuning. Red curves correspond to doing the meta learning and then doing the fine tuning. And then this is the number of the updates we take during the meta learning or the multitask learning stage. And then what we see is that in the case of the multitask learning, as we update more and more, the parameters or the model actually adapts too much to the source task. And then we see that it actually drops eventually in terms of the target task performance. But if you look at the meta learning, it never drops because it is never trained to solve the source task as well as possible. It never adapts fully to the source task. It's trained to be good at being adaptive, but it is not trained to solve the problem directly. So I think that's actually a really interesting thing. The difference is pretty small, but still we do see that trend quite clearly. And then, unfortunately, or the fortunately, I don't know which direction, because when there is a really small number of examples, the gap between the meta learning and multitask learning really grows. That's very apparent. But if you have moderate number of examples already, then there's absolutely no reason why you want to do either of these. You just train from scratch and then do a lot of dropout, and then that actually works pretty well. So that's one kind of, I don't know, unfortunate or the fortunate observation that we have made. So here's one example. So the interesting observation we made was that so in the case of Turkish, let's look at this. So there was a source sentence, and then that's the target, the reference target. And then this is after meta learning, and then this is right before any kind of fine tuning. So the meta learning has learned to do some kind of, let's say, translation, almost word by word translation. But the word order is completely messed up because it has never seen the exact syntax of the Turkish. So it has it does the word-to-word translation type of thing because we use that shared multilingual word embedding. But it doesn't know how to put things correctly. But after seeing only about 800 examples, it can very rapidly learn to reorder the stuff and then get the better translation. And then the similar thing happens with the Korean as well. So the Korean is final word and the language, and then before the let's say meta learning, it really doesn't know how to swap the word orders going from Korean to English. So it's really literal translation that is not that great, right? So the word included, word included, it got confused. But after seeing about 800 examples, it rapidly realizes that, okay, so the verb at the end in the Korean sentence should come all the way to the front in the English. These are cherry picked, by the way. So the ones from the first part, not cherry picked. These two are cherry picked. So yeah, it doesn't really happen always. You saw that the Korean translation, the blue score was like under 5. This has to be a cherry-picked example because it looks too good, right? It doesn't make any sense. There are so many unreasonable translations in the case of Korean to English. But so the conclusion here is that, okay, seems like meta learning or the MAML, the specific form of the meta learning, allows us to exploit many high-resource tasks for extremely low-resource target tasks. And then what we observe is that like in the machine learning and deep learning field, we are observing gradual shift toward the higher order learning, starting from, let's say, about 2012 or so. So there's a lot of work last year on the learning to optimize. So if you think about what SGD is, and then if you look at how the LSTM looks like, they do look quite similar. And then can you use the LSTM to find the learning rate and so on, so that it can actually optimize certain type of the problems much faster. And then also there is the work on the multi-agent modeling, where you're going to train an agent that is going to have inside it the simulation of the other agent. And then it's going to try to take into account how the other agent is going to be updated in order to update itself. And then there's been a number of work from the Google Brain on the neural architecture search, where you want to use some kind of RL or the evolution algorithm to figure out the neural architecture that's going to get you the best, let's say, generalization performance. I mean, hyperparameter search has been the big thing since, let's say, I don't know, a long time ago, but these days we do use a lot of higher order learning signal to tune the hyperparameters automatically, and it seems like there are more. So, okay, this is my final slide. 2 lessons that I learned. I think that was actually the title of my talk. The first lesson, I thought the sequential decoding of a sequence was the answer in 2014, 15, and 16 until very recently. And I also thought that the multitask learning, transfer learning was the answer to all those low resource language pairs, like until 2016, 17 again. But it seems like in both cases I was very wrong, and then probably I'm going to be wrong again. So, take any of this meta learning thing with the huge grain of salt, just to make sure, because I might change my mind, and then 2 years later I would show up again saying that nope, you don't do any of this, wrong way to go, right? The second lesson is that so in these 2 topics that I told you about, so in the first topic we tried the denoising criterion for structured output prediction, which was actually done quite a lot about 10 years ago when everyone was going crazy about the denoising autoencoder and so on, but everyone kind of forgot about it. But it seems like that is still useful, and then there are a lot of lessons to be learned from that era. And then also we use the second order learning instead of the first order learning, in a sense that we try to see what's going to happen in the future to tune our model. And it seems like there are many learning algorithms or regimes that are still out there that we haven't really explored much. And it seems like we need to try more things to see what we are missing out at the moment. And that's it. Thank you. And if you have any questions on the meta learning, please go ahead.
So one of the things that we did was initialize with universal lexical representation.
Yes.
So it seems like that is really important for this thing to work.
Yeah, so it is important. It is important because, first of all, most of the meta learning work so far have assumed that the input outputs always match across all those tasks. But in the case of translation, of course, we cannot go all the way to bit level or the character level, but almost never we have that kind of exact match. Of course, if we went for the character level and then stuck to all these European languages in general, we could have actually done it without the universal lexical representation.
So the multitask results that you showed, that also used.
Oh yeah, that's the very same thing.
Oh.
We only changed the learning algorithm. Yes.
One last question.
Yeah.
So in the first part, you sort of showed structured output prediction.
Mm-hmm. Yeah.
So in that case, you're using cross entropy as the loss. You use some structured loss.
Yes. So that's actually a really interesting point because I just submitted the NSF career proposal on that. If anybody's reviewing the career proposal this year, just to let you know, I think my proposal is really nice. But yeah, so the question that's a really interesting question. Question is that we use cross entropies here, we use cross entropies here. Of course, cross entropy is just one, let's say, loss function that you can use. There are many different ways, or you could even have the sequence-based loss as well. Now, especially this denoising autoencoder is effectively learning some kind of structured loss itself, right? Instead of trying to minimize the sequence loss directly, what it's trying to learn is that it's just learning to minimize the loss given some input, right? So it is doing the structured output prediction, but in an iterative way. Yeah.
So in the simulated learning thing, did you try cheating and actually directly optimizing on one of these tasks? Basically, is the way that you would need to optimize for fine tuning to a task that you're also using in the training phase a good proxy for actually an unseen task?
We actually tried that. So the question is that so for the simulated learning, if we use the actual target task during the simulated learning, would it get better, right? It does get so much better.
Okay.
Yes. Yeah. Yes.
So regarding the first one, the autoregressive combine, I was wondering to what extent the autoregressive modeling benefits from seeing the last produced word in these kind of problems, and to what extent this is also some sort of optimization hack rather than a modeling problem. So that if you have meta-learning, what you lack is some sort of steering idea that allows your model to optimize, and it's always going to trap very shallow things, right? To what extent the autoregressive is just an excuse to have this additional information during training that guides the overall optimization?
Okay, so first of all, so is it really beneficial to look at the future or the older context instead of only the previous one? It is actually important. It's not only this work, but like the last year at NIPS there was a paper titled Deliberation Networks. So what they did was to do the refinement with the autoregressive model, but just one stage of refinement. So their model has 2 decoders, and then what happens is that there's one decoder that's going to use the first encoder that uses the first decoder to get the first translation, and then the second decoder is going to get the translation from the first decoder as well as the source. And then they train them all together, and then they do show that there is a significant improvement. And then that was one of the important techniques that Microsoft research used recently when they claimed the human parity on the English-Chinese translation or something like that, right? So, and then that was a really important trick. So this seems to be, this kind of iterative refinement seems to be a good idea. The question is that, okay, is it a good idea to do it purely on this way? Or should we mix autoregressive model and this kind of refinement on top of that?
So if you have supervision in the different sketches or different internal representations, you still have that advantage of steering the training, right? You don't float what you said, you don't float the internal solution, you feed an error signal at each step. So it kind of works in the same way. Because I was wondering to what extent that is what drives the entire thing working or not.
So yeah, so I mean it's not in my slide, but in the paper, so between this, let's say, end-to-end training and then the denoising. Denoising is much more important. So if we ignore the end-to-end training, we can still get to almost a similar level of the performance with the end-to-end training. But if we do only the end-to-end training, it doesn't really work. So what I think is driving is this really the idea of the iterative refinement using the denoising criterion. Yes?
Have you tried the meta-learning in a setting where you don't have a single output target language?
So not in this paper. Yeah.
Going into English only is okay,
Yeah,
but
I agree. Yeah.
if I speak a very low resource language, would I prefer it to be into my language instead of English? Would it be possible to learn the parameters for the meta-learning if you had 7 output languages?
I think there is no reason why we cannot. I don't see the reason. So the only thing that we have learned doing this kind of multilingual translation so far is that it is not trivial to make this kind of model do well on the pair of languages that was not seen during training. So there have been a number of tricks and the techniques that have been proposed to to mitigate that issue, but I feel like I also had one paper on that, but I don't feel like we really have okay, this is the reason why it doesn't happen and this is the solution to that at the moment. So, and then my guess is that the same thing is going to happen with the meta-learning. It seems like that is not the issue with the learning algorithm, but rather about how we can constrain the representation so that there will be the maximal sharing across the different languages. And then that one doesn't seem like we have the solution. Or Jan might have it already, but.
Okay, this is kind of a hardball question.
Okay.
So remember when you visited us 2 years ago, you said, okay, the future is character-based models, I can go to bit-based models or stroke-based models. So what's your current thinking on that, and how does that relate to your?
Right. Okay, that is a hardcore question. Yeah. So 2 years ago, I did say, actually in the same room, that it's all about character level modeling. And then this is actually the same example from. Maybe this wasn't there, but anyway, okay, similar example from then. I still do think that it should be character level for any kind of modeling, but now when it comes to multilingual translation, it becomes, especially when you consider Korean and Chinese, it becomes a bit less trivial to to share the alphabet set across the different languages. So now I I do think that okay, in the production system, if I had to build a production system, the same production MT system, then I'm going to actually use the both the let's say subword and the character level simultaneously, and then that actually does help in general. But for the experimentation in the universities, I think subword level is so much more efficient, and that's why I think generally we tend to stick to it. So still, the character level, yes. 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 Okay. All right, I guess no more questions. Okay, well, thanks.